The next talk is a new standalone Mac construct called CMac. It's the work of Dag Wang. I hope I pronounced it correctly. Alexander Maximov, Patrick Ekdahl, and Thomas Johansson. So go ahead.
Okay, thank you for the introduction. I'm Bart Mennink from Lund University. I'm going to present our work, a new standalone Mac construct called SMac. This is a joint work with Alexander Maximov, Patrick Ekdahl from Ericsson Research, and also Thomas Johansson from Lund University. My presentation contains 5 parts. First, I want to talk about the background and then our design. And while in our design, we have some configurable parameters, so I want to talk about how we find out the best design. And then I want to talk about the aggregating mode to improve, which can improve the performance greatly. And later I'll show the performance and talk about the future work. Recent years have seen many research papers on 6G, and it is said that 6G will be ready for the commercial market by the early 30s. For cryptography, one of the situations is that we need faster speed and lower latency. In 5G era, it requires 20 gigabits per second. And in 6G era, unfortunately, we don't know yet. But it should be faster than 5G, right? And on Ericsson's blog, it is said that it could be several hundreds gigabytes per second. And last year, documentation from NGMN considers peak data rates range from 50 to 200 gigabits. Another situation is that we may need truncatable MAC. In 4G and 5G, 32-bit tags are used in radio link layer, and transport and application layer use 64-bit tags, and media applications use 32, 64, and 80-bit tags. This type of truncatable tag can bring more vulnerabilities because the attacker can ask the verification oracle to find the collision pairs of message and tag, even in non-respected scenario. For example, for G-hash, a single collision pair can break the cipher completely. So to meet the requirements, we propose SMac, which is based on the Snow stream cipher, the lower part, the finite state machine. Let's move to the left figure. Here we replace this modular addition with the XOR operation, which is more friendly to hardware, because our goal is to design a cipher that is fast and secure and friendly for software and hardware. And as a MAC algorithm, it should be able to absorb message blocks. Here we insert the message block into the 2 AES round function and also the XOR operation. And you can see on the lower left, there is a sigma, which is the byte permutation on 16 bytes. This figure can be used as a round function, and it can be implemented with 3 instructions only on Intel platform. The first one is shuffle instruction for the byte permutation, and the later two can be implemented as 2 AES-NI instructions. And we also noticed that this round function can be viewed as the right figure, which might be easier for people to understand it. And there are many similar construction in previous work. One is Jing and Nicolic's design and Roca's design, and also LUMAC, PettyMac. The main difference here is that we use the byte permutation, which can provide better diffusion, and with this better diffusion, we can reach a certain security level by using a smaller state. And there are many possibilities for this byte permutation. So they also provide more possibility of the designs. So later I'll talk about how we find out the best byte permutation here. Okay, now we use this round function in our design, and the whole cipher looks like this. is kind of sponge-based construction. In the initialization phase, we take the key and IV as the initial state and clock several rounds to reach to mix the states well. And in the compression phase, we absorb a message block in each round. And finally, we clock several dummy rounds again in the finalization phase to produce a secure MAC tag. For typical sponge-based construction, there is the capacity. So we propose another method to balance this property. We call it rate AB. You don't need to understand the equation quite well. The basic idea is to insert some dummy route after we absorb some message block. Let me take an example. In this paper, we propose SMAC 1 second and SMAC 3/4. For 1 second, it means that after we absorb a message block, we clock a dummy round. That is, we clock a round without absorb any message block. And in SMAC 3/4, it means after absorbing 3 message block, we clock 1 dummy round. And in the implementation, we can make it to absorb a constant message block. That's sufficient. For the security problem, before I move on to the best permutation, for this, there is a main security problem. That is the cohesion property of the internal states. This corresponds to finding the differential trail inside this compression phase from 0 difference to 0 difference. For the initialization phase and finalization phase, the attacker don't have any capability to insert value inside. So if we clock enough rounds, typically it's secure enough. So our work mainly focus on the compression phase. During the compression phase, yeah, the attacker can insert some message differences. Also relate to the differential attack. For example, in rate 1, we found this byte permutation. For the first byte permutation, it only has 9 active S boxes in a differential trail from 0 difference to 0 difference. In the second byte permutation, it has 20 active S boxes. So you can see there is a huge difference between different byte permutation. So we want to reach the best one. But there are in total 2 to the power of 42 byte permutations. If we want to test all of the permutation by SAT or MILP tools, that would be too much, too intensive, and I think it's infeasible. So we adopt another approach. We split this task into several steps. In the first step, we noticed that for 3 and 4 round differential analysis, it's very simple, very easy, that we don't need to rely on any SAT tool or MILP tool. So we implement our ad hoc method in C++, which is very efficient. So we run this program on all of the permutation. And finally, the result is that for SMAC 1, we have 73,000 byte permutation left with 20 active S boxes at least. And for SMAC 3/4, there are still 1.6 billion, but it's already much less. For this smaller number of byte permutations, we can start the SAT model or MILP tools to perform further analysis on it. But here, 1.6 billion is still too many. So we intensive task. And we found that after 6 rounds, all of the permutation have a property that the number of active S boxes is increasing. So we are sure that it should not be the best attack is usually around 5 round or 6 round. And after this stat and FRP analysis, we noticed that we still have around 10 to 20 byte permutation left. So then the final step is that we decided to perform a clustering effect analysis on the remaining byte permutations, because this round function is very simple and it may have some we want to make sure that we don't have this problem, and we want to get the precise all of the chairs and sum them up together. And finally, the result is that we select after all of the test, we select a permutation with probability about 2 to the power of minus 118 for SMAC1. For SMAC 3/4, we select 2 to the power of minus 152. For SMAC 1/2, we select 252. You can see the security level is increasing. And actually, this attack is the best attack among all of our analysis. So finally, we claim the security level for them as SMAC 3/4 has 152, SMAC 1/2 has 252 bit security. Now let me talk about the aggregated mode. I won't talk about too much detail. I won't go through too much detail about how it looks like. Instead, I want to provide an example about how it works. For this SMAC 1x4, after the initialization, we insert the index of each stream to prevent swapping attack. And after initialization phase, we generate 4 random states, and these 4 random states will be in the same register. Our aggregating mode aims to make use of a 512-bit register that is on modern Intel CPU, like those has AVX 512. And these 4 random states is in one register, and they can absorb message blocks then in each 128-bit part. And after that, we have a finalization phase 1, which combine 4 parts into only one 28-bit registers, and then do the normal finalization phase. Yeah, this is parallelization at the instructions level, and it greatly improved the since I have 8 streams, double of the previous figure. I think this design is currently the fastest design, but yeah, the security level is slightly lower than other design. Of course, sometimes it's a balance between them. For the future work, there are many possible directions, but I want to mention a fun fact here. That after checking all of the permutation, we noticed that there are only 2 permutations that have at least 20 active S-box, and all of the other permutations are very weak. So we are wondering that if there is a mathematical theory behind this type of design, that can we find out such a theory to derive the permutation directly? If we can find such a theory, then which is more secure and faster. And yeah, we believe that it will be much better for the 6G era. Okay, that's all. Thank you for your attention.
Okay, thank you. Any questions?
Thank you for your talk. I would have two questions. First, these two.
Are symmetric to each other. That's why we believe that there is some mathematical theory behind.
Okay. And my second question was, so basically you took a part of snow and improved it for your purposes. Would putting something like what you have built in snow improve snow?
Yes, could be. Actually, we are working on some new version of Snow and trying to improve the speed and also security. Yeah, we will publish maybe later when we have a good result. Thank you.
Any other question? Yes, over there. You can come next, Nakasu. Don't worry.
Yeah.
We focus on the differential trail,
Yes.
but maybe there's some other kinds of tech.
But we also take into account cube analysis and many random tests like cube testers. Yeah.
Okay, thank you.
So Kazu had a question in the front here.
Just a small question. So please go back to the benchmark slides.
Okay.
27 maybe.
This one?
So yeah, on the top, there's a G hash, and I'm wondering why it has a security level of 96 bits.
Yeah, I think it's written in the documentation. If I'm correct.
If I'm correct, I think it's 128 bit secure. Yeah, okay, that can be discussed offline. Yeah.
I could imagine they take the length into account, like a maximum length.
But it's length.
It's 2 to the 18.
Right?
Yeah, that's true. I mean, if you take 2 to the 32, you get 96. Yes.
Yeah,
but
yeah,
I agree.
but
32 is not 18.
But in the table that for S-Max case, that the security level is consistent with respective with the input ranks, right? So
yes.
I'm just I want to clarify.
Yeah, I agree.
Okay, thank you.
Yes.
Thank you.
Any other question? So I had one brief question actually. So this SMAC 1 times 4, 1 times 8. I think you also have 1 times 16 in the paper. They are more efficient, right?
And then I think there is a limit that if we reach.
Security level should degrade between 1 times 4 and 1 times 8 or not?
And we have a brief analysis following Farfalla because the XOR part is similar to Farfalla. And in Farfalla's paper, they also have differential analysis. And we understand that analysis also applies to our design. And after using the analysis, we noticed the attack cannot be low, it cannot achieve a better attack.
Okay.
So it's still 118.
Okay, good. If there are no other questions, let's thank the speaker and all the other speakers of the session again.